The idea of teleportation has always captivated the human imagination. We dream of instantly traveling vast distances, bypassing the constraints of time and space. Science fiction has long explored this concept, offering tantalizing glimpses into a future where teleportation is commonplace. One iconic example is the Star Trek franchise. Captain Kirk's famous command, "Beam me up, Scotty," instantly transports him from alien planets back to the Starship Enterprise. The process appears seamless, a shimmering effect, a dematerialization, and then reassembly at the destination. However, the fly presents a darker side to teleportation. A scientist's experiment goes horribly wrong, merging his DNA with that of a fly. This cautionary tale highlights the potential dangers of tampering with the very fabric of our being. These fictional portrayals, while entertaining, often gloss over the immense scientific challenges involved in teleportation. They ignite our imaginations, but rarely delve into the complexities of transferring matter across space. To understand teleportation, we must venture into quantum mechanics. The subatomic world defies our everyday intuition. One bizarre phenomenon is quantum entanglement. Imagine two particles sharing the same fate, no matter the distance. Einstein called it spooky action at a distance. Measure one, and you instantly know the state of the other. This forms the foundation for quantum teleportation. Scientists have successfully teleported information using quantum entanglement. This isn't the same as teleporting physical objects, but it's a crucial first step. The process involves transferring the quantum state of one particle onto another, effectively destroying the original state and recreating it elsewhere. Imagine having two coins, one in your hand and one held by a friend far away. You flip your coin and get heads. Instantly, your friend's coin, entangled with yours, also becomes heads, even though they didn't flip it. This is a simplified analogy, but it captures the essence of quantum teleportation. While this process doesn't transport the physical coin, it transmits the information about its state. In the quantum world, this information is encoded in the particle's quantum properties, such as its spin or polarization. Quantum teleportation has profound implications for secure communication. By encoding information in entangled particles, we can create unbreakable codes, as any attempt to intercept the message would disrupt the entanglement, alerting the sender and receiver. Teleporting information is one thing, but teleporting physical objects, let alone human beings, is an entirely different ballgame. The challenges are immense, pushing the boundaries of our current scientific understanding and technological capabilities. To teleport an object, we would need to record the quantum state of every single atom and particle that makes it up. This information would then be transmitted to the destination, where it would be used to reconstruct the object from scratch using new particles. The amount of information required to describe even a simple object is staggering. A single human body is composed of trillions upon trillions of atoms, each with its unique quantum properties. Storing and processing this information would require unimaginable computational power. Moreover, the act of measuring the quantum state of a particle inevitably alters its state. This fundamental principle of quantum mechanics poses a significant obstacle for teleportation. How can we accurately record the state of something without changing it in the process? Section 5. The energy barrier powering up teleportation. Even if we could overcome the informational and technological hurdles of teleportation, we would still face the daunting task of harnessing the immense energy required for such an endeavor. The energy needed to teleport an object would depend on its mass and the distance it needs to travel. The farther the distance and the larger the object, the more energy would be required. Teleporting a human being across even a short distance would likely consume an astronomical amount of power. To put this into perspective, consider the energy released by a nuclear bomb. Teleporting a person might require energy on par with, or even exceeding, such a devastating event. Clearly, we're nowhere near having access to such energy levels in a safe and controlled manner. Furthermore, we would need to find a way to channel this energy precisely to dematerialize and rematerialize the object without causing any damage. This would require an unprecedented level of energy manipulation and control. Section 6. The computing conundrum deciphering the quantum code. The computational power required for teleportation would dwarf even the most powerful supercomputers we have today. We would need computers capable of processing and storing unimaginable amounts of information at lightning-fast speeds. Imagine a computer that could store the entire contents of the internet on every single atom in your body. That's the scale of data storage and processing we're talking about for teleportation. Even with Moore's law, which predicts the doubling of computer power every 2 years, we're still many generations away from such computational capabilities. Moreover, we would need to develop entirely new algorithms and software capable of handling the complexities of quantum information. Traditional computing relies on bits, which can be either 0 or 1. Quantum computing, on the other hand, utilizes qubits, which can exist in a superposition of both states simultaneously, exponentially increasing computational power. Developing quantum computers capable of handling the demands of teleportation is a monumental task, requiring breakthroughs in material science, quantum algorithms, and error correction. Section 7. The teleportation paradox. Are we still ourselves? Teleportation raises profound philosophical and ethical questions. Would the individual who arrives be the same person who left? The process involves destroying the original and recreating it elsewhere. This raises the question of identity and consciousness. Is our consciousness simply a product of our physical makeup? Teleportation could be a form of death and rebirth. The person arriving would be a perfect copy, but not the original. This raises ethical concerns about creating and destroying conscious beings. The teleportation paradox forces us to confront fundamental questions about reality and consciousness. Quantum communication, unbreakable codes and secure futures. Quantum mechanics, particularly entanglement, is revolutionizing communication. It promises unbreakable encryption for secure information transmission. Imagine governments communicating without fear of eavesdropping, financial transactions secure from hackers, and personal data truly private. This is the potential of quantum communication. It's already being implemented in real-world applications. Several countries have developed quantum networks. The future of secure communication lies in quantum mechanics. Section 9. A world-transformed teleportation and the future of humanity. The advent of teleportation, if it ever becomes a reality, would usher in a new era for humanity, transforming society in profound and unpredictable ways. The way we live, work, travel, and interact with the world would be forever altered. Imagine a world without cars, trains, or planes. Commuting would become instantaneous, allowing people to live and work anywhere in the world, regardless of distance. Tourism would flourish as people could effortlessly visit distant lands and experience different cultures. The environmental impact would be significant, as teleportation would eliminate the need for fossil fuel-powered transportation. Pollution would plummet and the fight against climate change would receive a much-needed boost. However, teleportation would also bring its own set of challenges. The economic and social implications would be vast, potentially leading to job displacement and widening the gap between the haves and have-nots. The potential for misuse is also a concern, as with any powerful technology. Section 10. Ethical considerations. Navigating the uncharted waters of teleportation. The ethical implications of teleportation are as vast and complex as the scientific challenges. We would need to grapple with questions of access, regulation, and the potential for misuse. Who would have access to this technology? Would it be available to everyone, or would it be restricted to the wealthy and powerful? How would we prevent teleportation from being used for criminal activities such as smuggling or terrorism? The ability to instantly transport people and objects across vast distances raises concerns about privacy and security. How would we prevent unauthorized access to restricted areas? How would we ensure the safe and ethical use of this technology? These are just some of the ethical dilemmas we would face in a world with teleportation. It's crucial that we engage in thoughtful and informed discussions about these issues before such technology becomes a reality. Section 11. Conclusion: the teleportation revolution. A distant dream or an inevitable reality. Teleportation, once a science fiction dream, is now a tantalizing possibility. Human teleportation remains distant, with immense challenges. Quantum mechanics, especially entanglement, is revolutionizing communication and computing. Quantum communication promises unbreakable encryption. Quantum computing could transform medicine, materials science, and AI. Exploring quantum mysteries may bring teleportation closer. The future of teleportation is full of potential. From science fiction to reality, teleportation faces many challenges. Unlocking teleportation could forever alter human history.